The Markov chain Monte Carlo method is actually, in many ways, the bedrock of a lot of tools in things like machine learning and computer-intensive statistics. And it runs off this idea of estimating an equilibrium distribution from a Markov chain simply by running that Markov chain, simply by running it and generating realizations of a variable through what state the underlying Markov chain is in. Now, the real trick of it is that we can set up Markov chains that are easy or easy-ish to simulate, which have an equilibrium distribution, which would be very difficult to simulate from. So the idea is that I set up a Markov chain whose equilibrium distribution is equal to the distribution that I'm trying to sample from, and then I simply run that chain. And once I'm sure it's in equilibrium, I'm sure that the observations or the states that my Markov chain is in can be regarded as samples from the equilibrium distribution. Now, I don't really care what the distribution of those samples is, but in the limit, then I want to make sure that it's reached equilibrium or can be approximated by that. So I can say that once I start to get it running long enough, every time the chain moves, I'm getting draws from the distribution which we want. Now, there are many variants on MCMC algorithms. So here we'll focus just on, well, I was going to say the original, but it's the original with a slight amendment, which is the Metropolis-Hastings algorithm. And it was developed by nuclear physicists working at Los Alamos. In fact, some of the authors on the original paper you may recognize as names in the film Oppenheimer. Now, it's named after a man called Nicholas Metropolis, which is two things. An incredibly cool name to be called Dr. Metropolis. Anyway, I don't know why his name and his name alone was attached to the original algorithm, the Metropolis algorithm, when he was one of 5 authors on the paper. But it was subsequently refined slightly, and we'll discuss that later, by Hastings. So now it's commonly known as the Metropolis-Hastings algorithm. But Nick Metropolis himself, he looks a little bit like a sinister version of Walt Disney, but that's Metropolis. The way the algorithm works is not actually sampling from the distribution I want. Let's say I have a distribution that I'm trying to sample from, P of X, which is difficult. But I can approximate it to G of X. Now, G of X is a simpler distribution to sample from. I can set up a Markov chain with that equilibrium. And what I want to do is I want to sample from G of X and then edit or throw away some of the realizations from G of X until what I'm left with can be regarded as realizations of P of X. So we call G, in this case, the proposal distribution. So at each step, unlike a usual Markov chain where I would say, make a move, A goes to B, make a move, B goes to D, make a move, D goes back to B. What happens is that the G, the proposal distribution, suggests making a move, and then I have to look at the distribution that I'm aiming for, and then make a random decision as to whether I want to accept that proposal and do what the proposal distribution said, or whether I want to look at my target distribution, what I'm aiming for, and say, no, I will reject that move. So what we actually have, we have an acceptance probability of each move. So if I'm in state X and it proposes going to state XP, I need to calculate this probability. Now, in a future video, we will derive exactly where this has come from. What I will say initially is ignore the back terms, the G of X given XP divided by G of XP given X. If I just look at the front terms, it's the ratio P of xp divided by P of x. So in other words, how probable is my proposed move in the target distribution, P of xp, divided by how probable is my current move in the target distribution, P of x. And if that ratio is bigger than 1, then I'll do it. And if that ratio is smaller than 1, then I will accept the move with that probability. Now, because this would be biased by if the proposal distribution was suggesting a lot more moves from x to xp than the other way around, then I have this sort of correction factor of the ratio at which it suggests going x to xp versus going xp to x. And that actually back term here is the Hastings contribution. The original Metropolis algorithm didn't have that. It had a slightly tighter set of conditions on what I could choose for the proposal distribution. So if I accept the move only with this probability, then it will always accept moves which are to states more likely in the target distribution. And if not, then it may or may not take them. If it's proposing an impossible move, then P of xp is 0 and it will never take it. If it's proposing a slightly less likely move, so P of xp is less than P of x, then it has to make a random decision as to whether or not it will take that move. So the way this works is, well, I pick a starting state at random. I then propose a move by picking, if I'm in X, what does the proposal distribution suggest? It says, hey, go to XP. And then I would generate a uniform random number between 0 and 1. And if my uniform number is less than this acceptance probability, then I accept the proposed move and I move from X to XP. Otherwise, I reject updating, replacing X with XP, and my X stays the same, and I just repeat back from step 2.